Good afternoon. Now we're going to proceed to the seminar on the pattern recognition. We're going to implement all the three methods of pattern recognition that we were talking about in the last part of the lecture, and we're going to implement them in application to the recognition of lines. We're going to use these two examples, these two videos. One of them is a video of points, dots, that were drawn on the whiteboard, and they pretty much lie on a certain line without much of the inliers here and there. And the second video is intentionally filled with outliers. Oh, excuse me, I meant outliers. So it's full of outliers, and the first method, the least squares method, will show very poor performance here. It will almost cease to work in any meaningful way. I have prepared some code here, and first of all we are going to have a quick glance on it, and after that we are going to implement these three key methods. Those were prepared in advance. The first is for least squares method, the second is for half transform, and the last one is for random sample consensus. So, what did I prepare in advance? First of all, it's the mask obtainment procedure. We have to process the input frames so that we can extract the bounding boxes or the positions of the dots on the whiteboard. And now we can check how does this mask obtainment work. Here you can see these two frames. The right one is the mask, obviously, and on the left we are marking with the red bounding boxes those areas of the mask that fit our requirements to the dot on the whiteboard. So it's not supposed to be very small, it's not supposed to be very big. Here on the left you can see that some of them do not appear to be in the proper shape, so to say. They are too much elongated, and we discard them because, yeah, the same goes on the left top. We discard them because they are clearly not the proper dots on the whiteboard. So this is the classical vision pipeline. You are most probably already familiar with it, so we will take just a quick glance about what's going on here. First of all, we blur the whole image. Its resolution is regular Full HD, so it's quite big, and we can use the blurring kernel of 5 by 5 pixels. That's fine. After we have removed some of the noise, we can proceed to the mask obtainment, and believe it or not, I have just taken these values from my head without any tuning, because it just makes sense. These lines in the video, they have a distinct blue color, and this makes it possible to detect the objects that were drawn by this marker on the whiteboard. So here I state that the mask will consist of the pixels that fit in between of 0, 0, 0 in each channel, and that have relatively low values in the red channel, in the green channel, and up to high values in the blue channel, so BGR. And it didn't require any tuning. Probably with the proper tuning we can get rid of some of the false positive, but we will not do that because we're lazy, partially in order to demonstrate that the least squares method doesn't perform well in the presence of the noisy data. After we have done that, we are performing regular analysis of the connected components. We extract the number of the components, the labels mask, the statistics, and we are starting the assembly of our data. It will be stored in the list. We're going through all the objects except for the background. And here, if the object is greater than 10 in terms of the area, smaller than 400 in terms of the area, if its width divided by height is less than 3, and the same for the inverse ratio, we consider it to be appropriate. If a certain bounding box fits our requirements, we append its coordinates, or to be precise, the coordinates of the middle of its bounding box, in the list of dots. Here we draw this bounding box on the frame, and as the output of the function, we return the mask and the list of the dots. Here you can see the remains of the debugging process, so I just manually marked some of the points, just 3 points, and I was trying to fit a proper curve, proper line to them when I was debugging. This is the first function, and actually the most complicated one from those that I have prepared. The second one is just drawing the line, given its slope, its free coefficient, minimal and maximal x coordinates, in between of which we are going to draw the line, the color, and the frame. So nothing special. We are calculating the y's, y sub 1, y sub 2, and we are drawing the line, not forgetting to transform it into the integer, because cv2.line has only integer numbers as its input. The next function is drawing the line just in another parameterization with angle theta and the length of the normal vector from the origin to the line. And here we are basically using the same drawLine function, but we just calculate the regular representation of the line with the slope and the constant. So nothing special here. The next function here is just for convenience. We have to use the same code in all our methods, in all 3 methods, least squares, half transform, and transect. We are interested in the minimal and maximal coordinates, where the data belongs to. And we want to find the whole number of the data points. Here, just for convenience, we repack the data into 2 separate arrays. We, as a result of this function, have an array of x values and y values. That's it. The next function is the function that calculates the distance from the line that is set by the slope and constant to a point. Here it requires some trigonometry or some, I don't know, vector algebra, whatever. So you can double check that while pausing the video if you're interested in doing that. But it's just a calculation of the distance. It's for Ransack. We will need that in order to evaluate the number of the inliers in the data set. The next function is the transfer of the representation of the line from the slope and constant to the length of the normal vector and the angle. Here we are using some vector algebra again, or trigonometry, as you will. And after that, we basically have to write down the code for these 3 methods. And if we will do it correctly, we will be able to extract the line from the data using those methods. We can compare them to each other. We can talk about their applicability for a bit. So let's start with the first method, least squares. Here we conveniently have all the formulas, and we will basically need only the letter 2, these ones, As you can see here, I have already prepared a hat, b hat, and x minimum, x maximum already calculated. So we basically need only to rewrite these formulas in the code. So you can pause the video and go along, I guess, if you want to. So b hat is equal to something, something. How can we do that conveniently? Well, first of all, we can calculate all the necessary averages. We can calculate the average of y's, the average of squared x's, the average, or not the average, the sum, excuse me, the sum of the y's times x's, and so on. So let's do that. We can call them y, yeah, just y sum. Or let it be just y for clarity. So y is the sum of y's. X will be the sum of x's. xy will be the sum of x times y, because those numpy arrays, they support element-wise multiplication. And the last thing that we need is the x2, let's say, x squares. So this is the sum of squares. And we can do it like this. So let us start assembling this monster of a formula. First of all, it's y times x squared minus xy times x, times x. And here we have n times x squared minus x to the power of 2. I said minus, okay. So that's b hat. A hat is supposed to be in the brackets xy minus b hat times x divided by x2. So this is the a hat. I think we're done here. So we can return the result. Let's call this function. This call is actually already prepared, so we can uncomment that. And we're going to draw the line. And if everything is correct, if there are no mistakes, now we are going to see the line that we have fitted with the least squares method. Yep, it's working perfectly. Let's observe how does it perform. And there will be a moment, let's wait for it, when this method will start failing. So we can discuss that for a matter of clarification. Now it's fine, but pretty soon it's going to fail. Yes, here. So there are some false positives over here in the corner, and they lead to this model giving just gibberish data. And if an outlier is somewhere at a very distant position from the real line, the output of this model will not make much sense, because this model takes into account all the data, including the outliers. But if there are no outliers, actually the result is pretty solid. You can tell that this line here represents the data pretty well. And the method itself is, I should say, rather straightforward, so nothing special here is just 10 lines of code, and we can detect lines in the image. That's pretty good. So we can generalize this least squares method to the polynomials of higher orders. Let's say we can do the same for parabolic functions, for the functions of the power of 3, for the polynomials of the degree 3, and so on. And there's even a general solution to that, but we are not going to cover it now. What we're going to do now is we are going to proceed to the half transform. Now we're going to demonstrate that with the noisy data, this least squares method doesn't give us any meaningful results. Here, as you can see, this line is just some random line that is going, well, I can say that somewhere in the middle of this blob of noisy data, and that's it. One way to deal with this situation is to perform some kind of filtering. Maybe we can deny all the points that are distant from big clusters or something like that. But generally speaking, it will be out of the scope of the least squares method itself. It will be some kind of preparatory work, some preprocessing. There are methods of supplementing this approach with some judgment about points being noisy, not noisy, but we are going to proceed to the method that is, so to say, honestly robust to the noisy data, which is half transform. So I'm going to comment this function call. I'm going to comment the least squares method, and we are going to proceed to the half transform. So here I have prepared the sketch of the function, and what's going on here? Well, first of all, let's take a look at these functions' inputs. The first input is the set of data points. The second is the angular step that we were talking about in the lecture. So on the left over here, we can see this exact angular step. The angular step is the angle between two lines, two neighboring lines. The third parameter is the spatial step, or the discretization along the spatial dimension in the space of the parameters. It's the distance between two lines at which we start to distinguish them differently. The next parameter is the maximal possible coordinate along the spatial axis. So that's the maximal length of the normal vector to the line. If the line is further, we neglect it because, let's take a look over here. So we set this parameter to be equal to the diagonal of the frame. If the line is further than that, we're not really interested in it. And the last parameter over here is just the frame. That's for visualization. Here we are calling the same function that repacks the data in a manner that is suitable for us. And here I have prepared the function to visualize the accumulator, or the parametric space, this thing from the second slide on the half transform. And what we're going to do next is we are going to create this accumulator. We're going to create it. We're going to go through all the points and fill this accumulator. And, well, after that, we're going to visualize it. And the last thing that we need to do is we have to find the angle and the length of the normal vector, the r, that represent the most probable line or the answer of the whole procedure, the result. So we're going to create an empty array of a certain size, and this size will be, it will be an integer from math.py divided by the angular step. This is the first dimension of the accumulator. The second dimension of the accumulator is the, well, it's better to, yeah, it has to be an integer. The second dimension is the maximal coordinate divided by the spatial step, or the discretization step. So, divided by d. And this array, this accumulator is a single channel array. The last thing that we have to specify is the data type, and the data type could be uint8, just for visualization. It will be not that big, and math.py divided by 0.05, it's like 60 nearly. And this one will be, let's say, 2000 something divided by 5, so that will be 400, 450, something like that. It's just good to keep track of the orders of magnitude of different values over here. So we have created the accumulator, and after that we have to go along the whole data set while filling the accumulator. Okay, so x of the dot and y of the dot, or of the data, we can store just the x and y of the data point number I in them for convenience. And after that we have to run a for loop that will go through all the lines as it's drawn over here. So it will consider first a line that is, let's say, horizontal, or almost, okay, just from the beginning, then the next line will be with an offset of the angular step, and so on and so on and so on. And we have to calculate for how many times actually do we need to do that. And yeah, actually it's given here already. So let's write it in a more clear way. So angles number, like this. So the first dimension will be angles num, and the second will be, let's say, spatial num, why not? And here this for loop will run through all the angles. And the angle over here will be equal to the index times angular step. And another thing that we need to do is we need to start from the vertical lines, so that at the very beginning we are able to sustain the origin, let's say, let's put it that way, to the left of the line, because it makes us able to disambiguate between two different situations. It's just more convenient in terms of the programming, because if we're dealing with some rotations, some angles, if a line has a certain angle, it's the same line that goes with the angle that is greater by math.pi. The whole range of the angle of these lines will be pi, not 2 pi, because that will be too much. We will get some unnecessary false positives, and here we are doing precisely that. So the whole range, we are dividing this whole range by the angular step, and here we're going to subtract math.pi over 2 from it, so that the angle will run from minus pi over 2 to plus pi over 2, basically. The next thing that we are going to do is we have to calculate the r, the length of the normal vector. And we have somewhere the function, yes, r theta by ab. And here a is given by math.tangent of angle, and b is given by, let's write a comment over here. So the regular form of the line equation is the following: ax plus b, and thus b is equal to y minus ax. And the x and y that this equation has to take into account is the ones that we have over here. So we can use the function r theta by ab, because b here is yd minus a times xd. You can even remove the comment. And r times subscript, well, we have the theta already. It's the angle. We don't have to calculate that again. And, well, if we will do that, there's an arctangent here, so that's the same. Anyways, we are going to call this function, and it will give us the r, the length of the normal vector. And after we have done that, we only have to increment the value that corresponds to this line in the accumulator. The line that is set by the angle and this length of the radius. So, accumulator of something something in the brackets plus equal 1. We're going to increment that. Well, what's going on here in the brackets? Here in the brackets, along the first dimension, we're going to have just I, because, what? Wait. No. We have to substitute the indices. Here it's going to be j. Sorry for that. And so here is going to be j as well. I have almost fooled myself. And here we are going to divide b by the spatial discretization size, or the cell size, and that's the integer division, or the division so that the result is an integer, basically. And that's it. So let us now visualize the accumulator. After that, we are extracting the indices, where the maximum belongs to, and after that we are basically returning the proper parameters. So let's try running this code. In order to do that, we have to uncomment this function call. And here we are using draw line by r theta, so we are visualizing the line in different parameterization. Nope. Okay. Wait, what? Ah, okay. Maybe I was too fast to think that it will work this way, but with an integer, it should be fine. Okay, not really. Okay, so let's debug. Let's try to find out what's going on. I suppose that something is missing over here, so I'm going to print b. I'm going to print... Wait, what? Why b? No. I was wrong. Here we have to insert r instead of b. Sorry for that. It was my bad. And yes, now it's better. Now it's working. So what do we see here? Maybe the most impressive thing is that it's working, but I think that the most impressive thing is the accumulator. So can you feel the sheer coolness of this thing? Each and every point in the input data is mapped into this strangely curved structure in the space of the parameters. And after that, we're choosing the brightest spot, the brightest point over here. And it always happens to be a good approximation of this line on the screen. Well, there are some bits of maybe mistakes here and there, but those are not really the mistakes. These mistakes, they come from the computer vision part of the procedure, or so to say, it's better to say from the classical pipeline, not the pattern recognition pipeline. It's the fault of the mask construction procedure, not the half transform problem, because some of the areas, some of the dots appear on the left on the screen, but generally speaking, this method is working just fine. Here we can count on, let's say, 0.6 of inliers, and the rest are clearly outliers. They're just noise. They are all over the place, and the method is capable of handling that just perfectly. So by yourself, try to play with discretization steps. Try to notice the difference when the discretization step is small, when it's big. How does this affect the performance? How does this affect the shakes and noises of the line? What is happening with the runtime? So try this out for yourself. And maybe you can try implementing this half transform for circles. Why not? Last but not least, we are going to implement the random sample consensus algorithm. Here we are going to use basically the same frame. Here we are repacking the data so that it's convenient. And one thing that we have to calculate is this thing, the number of the samplings that we have to perform. So m here will be equal to, now we'll have this boring ratio. Actually, the base of the logarithm is not important because we can change it arbitrarily. And in the denominator, we are going to have math.log2 of 1 minus alpha to the power of how many? 2, because the lines are two-dimensional objects. And this is the number of the samples that we have to take from the data. And let's check this formula just somewhere. So, how many times do we need to sample in order to get a certain probability of success? I'm going to comment the half transform call, and here I'm going to just steal this whole thing. No, I don't need the epsilon. Okay, that's later. What I need to do is I have to specify the expected probability. Let's say I want the probability of success to be equal to 0.9. And oops, should be 1. Okay, and alpha, the share of the inliers, will be, let's say, 0.6, which is really the reasonable value for our type of data. And I'm going to print the number of the subsamples that we have to take. Okay, so that's 5. Okay. Is there math.ceiling? Okay, yes, math.ceiling. That's the smallest integer that is greater or equal to the number. Okay, and what do you think will happen if I will increase the expected probability of success? Let's say 0.98. What will happen with the value? Let's check. It has increased, and that makes sense. We want the probability of success to be higher. The method demands us to sample more. And now what is going to happen if I will decrease the share of the inlier points over here? Let's say I will decrease it really harshly. Let's say we have only 40% of valid points and the rest are just noise. What will happen here? Okay, we have to sample more again. And this totally makes sense. I'm just demonstrating that this formula behaves in a reasonable way. So I will copy-paste this thing with ceiling, because that will exclude the probability of me passing some floats where we don't need them. Okay, so for I in range of the number of times that we have to sample, first we have to take a subsample. Second, we have to create a model. And third, we have to evaluate the model. Of course, also we need some r hat and theta hat. Whatever. And yeah, we'll create the number of inliers later. Let's move on to this upsampling. Well, that's pretty much straightforward, because we only need to get some random point from the dots. NumPy or NP random rand integer, of n. And with P2, we are going to do exactly the same. So after that, we have to create a model. Subsampling is done. It's pretty easy. So here, we are going to first check if we can actually construct a model from that. And if we cannot, we have to quit. We have to resample. So the first situation that doesn't fit our purposes is the first point being equal to the second point. We cannot really construct anything from the single point. And another thing is coming from the fact that we are going to use a regular way of representing lines. Just for simplicity, well, there could be better, more elegant ways of doing that. But we are going to represent the lines with the slope and the constant. So in such a way, we cannot represent vertical lines. And if the x coordinate of the first point is precisely equal to the x coordinate, the 0 component of the second point, we will skip that. We will draw and just go resample once again. So after we are happy with that, if we will not divide by 0, we can now proceed to the slope calculation. So the slope is clearly P1 of 1 minus P2 of 1 divided by the difference of x coordinates. And after that, we have to calculate the b coefficient. So we can use the same code as here. B is equal to this formula, so it will be, let's say, P1 of 1 minus 8 times the x coordinate, so it's P1 of 0. We have A and B. Great. And after that, we have to evaluate the model. So we have to calculate how many points from the data do indeed fit into this model. We are going to do that with this epsilon parameter, and here in the slide is given, well, here it's given as delta, but that doesn't make a difference. And here we're going to use this function, calc distance, that is calculating the distance from a line to the point. We're going to call it in a loop, actually for j in range, the number of the data points. We're not concerned with discarding the points that we are building the model by, because that will not make much of a difference. I mean, these points, they're always in layers, but that's always the case, so that doesn't change the outcome, the result. And here, yeah, basically we have to calculate the distance from the line that is set by these parameters to the data point number j. After that, if the distance, the current distance, is smaller than epsilon, this means that this current point, number j, is an inlier. Great, so we can increase the number of the inliers that correspond to the current model, but we don't have it yet, so let's create a variable for that. let's say, yes, just inliers number. Okay, I will write num, because I'm lazy, I didn't want to do that, but let's do it just for clarity. Okay, so just it's inliers number plus equal 1. And what we need to do next is we have to refresh the answer or the result. We have to modify it if the current model has, let's say, broken the record. If it has the biggest number of inliers among all the models, we have to just reset the maximum or the best model. Okay, so here I'm going to create another variable that is maximal inliers number. So the maximum number of inliers is 0 for this trivial model. And here we have to update it. So if the maximal inlier number is smaller than inlier number, we have to update it. We can do it like this. And also we have to update r hat and theta hat. Well, we have to calculate them. So we can use the method r theta by ab in order to obtain these values. We have a and b already. They're given here. So, well, we can actually do it like this. R theta and that's it. That's the random sample consensus. So let's try it out and let's debug it if something is missing. I think we can print the number of the samplings later if we need that. Here I'm going to just uncomment the function call and the drawing of the result. Okay, that is not working. What? Calc distance dot of dot s of j. Okay, that makes sense. Yep, that's the random sample consensus. As you can clearly see, it's not perfect by any means. So the results are shaky, more or less, but still it's working. And well, here we have set the desired probability to be quite high. Actually, it's performing worse than with this probability, but that's because here in the video we have some lines that, well, we have some parts of the noise, but that actually reminds lines. And we can adjust the parameters, we can adjust the thickness of the corridor or the epsilon parameter in order to neglect, or not to neglect, in order to deal with these effects. So the parameters that we have is the epsilon number, the desired probability, and our estimate of the number of inliers, or the share of the inliers in the video. So that pretty much finalizes our seminar. We have implemented by hand three methods of pattern recognition: least squares, half transform, and random sample consensus. All of them have their own strengths and weaknesses. Random sample consensus is simple, and it's perfect for the cases where no harsh noise is present. Half transform can deal with really harsh noise being present, and for this exact case, it's my own choice because of just the beautiful visualization of the accumulator over here, because to me this seems to be beautiful. And well, apart from just being beautiful, it's working. So this half transform is working with very noisy data. And if we will have to deal with the high-dimensional objects like ellipses or, I don't know, tables, we will have to use random sample consensus, which fits for various types of objects that could be set by a number of parameters. For example, we can, with the help of RANSAC, we can even find out the transform matrices when we are trying to calculate the change of the position of the camera in the scene. So this is the thing that could remind you of simultaneous localization and mapping or visual SLAM, something like that. So the applications of RANSAC are not limited to the recognizing of the lines and circles in the images. It has a very broad range of different applications, with some of them being the estimation of the transform matrices. That's it for today. Thank you for your attention.